it's not my slides. There's really something written over here, right? All right, so this is, yeah, I couldn't fit the new in the regular font, so I had to find some thing. So there are some locally decodable codes from lifting, and I'll explain what these things are. This is joint work with a PhD student of mine, Alan Guo, who's at MIT, and Swastik Kopparty, who's now at Rutgers. So let me start with some basic notation, which we will set up and then go from there. So we'll be considering codes, linear codes over a finite field. So f sub q denotes a field of size q, and these will be code words of length n. So n is called the block length, and the sort of classical parameters associated with error correcting codes are the rate and the distance. To introduce the rate, you say that the dimension of the code is sort of the length of the message that you can encode over here, and the rate of the code is just the ratio k over n, and we want this as high as possible. We also want the second quantity as high as possible, which is the relative distance, the normalized distance of the code, which is the minimum over distinct code words x and y of the fraction of coordinates in which x and y differ. Okay, so delta of x y is a fraction of coordinates where they differ. So these are standard parameters, and I will just sort of assume everybody is comfortable with them. And whoops, it's flying along. The basic algorithmic tasks that are associated with error correcting codes, and we will be talking about variations of these, are encoding, which would say given some message and given that the code has dimension k, it's good to associate the message with a point in fq to the k if you want. Map a message to some code word. So this would be the encoding map. We won't be thinking about it at all. So that's there's Swastik, with whom this was joint work, and hi Shubhangi. Whoops, what's going on? Sorry. The two more sort of tasks of importance to this particular talk are testing, which given a vector x you want to decide if it's a member of the code, or correcting, which says given x which is not a member of the code, find the nearest code word y to x. Okay, so these are the basic tasks. Now what we are going to be talking about are locality, locally correctable and locally decodable and locally testable codes. And where do these come from? These come from this general field of sublinear time algorithms, where you often want algorithms that run in time which is much less than the length of the input or the length of the output. If you want to do that, you would have to assume there's some way of accessing the input which is not sequential read access from left to right, and so you assume random access to the input. So you give me a coordinate I, and I should be able to figure out what is the ith bit of the input. And similarly, you would provide only random access to the output. So rather than I implicitly give you a vector or a long sequence, but you say, look, I want the ith location, I'll be able to compute it efficiently for you. Okay, so these are the general paradigms in sublinear time algorithms. And given that you are only accessing an input by random access and probably not accessing all of it, it makes sense to say, well, what I'm going to be computing for you, if you want to compute some function f on some input x, you might actually end up computing f on some x prime which is close to x. Okay, and in general, does this make sense or not? Well, this is all that can be done. So you have to figure out whether this is good enough for you or not. In the context of error correcting codes, this turns out to be a very, very reasonable model. So in the context of local of error correcting codes, what are the basic tasks? The encoding task unfortunately cannot be done locally. It's just not the kind of operation that can be supported locally. On the other hand, testing as well as correcting can be done locally, and so let's look at the testing and the correcting problems, and this is what we'll be looking at today. So locally testable codes are those that can be tested efficiently locally. Local simply means that the number of queries to the input is small. It's not in some geographical neighborhood. It's just the total number of queries is small. So we want to decide if some vector x is in the code probabilistically, and which means I'll be given random access to the coordinates of x, and I will be saying yes or no depending on whether it is in the code or not, but given that my answer is often going to be correct for an approximation to the input, what this really means is that I will be saying yes, I may be saying yes even if x is not in the code, as long as it is very, very close to the code, okay. And I will formalize the distances and measures in a minute, but this is what is allowed in this sense. So you want to reject things which are far, you want to accept things which are in the code, and in between there is a gray region, okay. You can do whatever you want. Similarly, locally correctable codes, this is the concept I will be talking about today. For those of you who have heard the phrase locally decodable codes, this is a slightly stronger concept, but this is all I will be talking about today, and many times I will sort of confuse results about locally decodable codes and correctable codes, but if I can give you good correctable codes, then there are good locally decodable codes associated with it, not the other way around, but this is what we will be talking about. So in a locally correctable code, these are codes which have sublinear time algorithms for correcting. So I give you a vector x, but it is not a code word, there is some nearby code word y, and I would like to be able to compute this y locally. Without accessing all of x, I would like to be able to find out what is y sub I, okay. So this is what local correction means, okay. Any questions so far? So there are two parameters that I will associate with all of these codes, sort of an error tolerance kind of a parameter epsilon, this is some loss parameter, let us say, and the locality parameter L. The locality will be a function of the length of the words that we are working with, and we will say that a code is a L epsilon locally testable code, LTC, if there is a tester probabilistic algorithm which makes oracle access to this vector x, and it will accept code words with probability 1. We will insist that there is no sort of error in this direction, it is one sided error. On the other hand, when you have a vector x which may not be in the code, then you reject it with probability some epsilon, this epsilon times the distance, the relative distance of this x to the code. So what fraction of x do I have to change to get a code word? You look at that quantity, you multiply that by epsilon, and you should be rejecting with at least that much probability, okay. So this is the expectation. If epsilon is a constant, then I won't mention it, and in general I will sort of quite often talk about just the first parameter alone, but really we should be looking at both of them together. L over epsilon may be an even nicer number to be looking at, but we will be relatively, we won't be too careful about what these numbers are, though this is really what we want to focus on. Now the corresponding concept for a correctable code would be, again, you make L queries, so you are given access to some vector x, but it is not a code word anymore, it is something that is close to some code word, and we do not know what that close nearby code word is. That is what we would like to find, and your decoder or your corrector should be able to find it. Sorry, I am calling it a decoder, should have probably called it corrector. And this algorithm D should make L of n queries to this vector x. It is given oracle access to x and the coordinate I where you want to compute y sub I, and it should be able to compute y sub I with high probability, and once again you are allowed to make some errors. So there is some probability with which you may output a decoding which is not y sub I, but that probability should be small. It should be bounded by two things. One is the distance of x to this word. If this distance happens to be large, then you do not necessarily output it, and now you divide it by epsilon, this number, to say, look, okay, your probability of being wrong might be even larger than the thing, okay. So yes, Clem?
Probability here over I, or it's only over internal?
Oh, sorry, this should not be probability over I, thanks. This should be probability over only the internal random coin tosses of the decoder, and should not be a function of the x or the I or the y, okay. Sorry, this should have been probability over just whatever coins the decoder tosses, but I is a worst case input. Sorry, thanks, that was a mistake there. So as I mentioned, we will often ignore the epsilon and just talk about what kinds of locality can be obtained in various codes and so on. So this is the general paradigm, these are the kinds of codes we want to construct, And the most basic example of a locally decodable or a locally correctable or a locally testable code turns out to be coming from multivariate polynomials, and let me tell you about this. So far Avi is sort of looking, this is the same talk that I've heard so many times. Not quite new, right? So the message is the space of messages we'll associate with a set of multivariate polynomials, and their encoding will be just evaluations of this polynomial everywhere. Okay, so there's suppose you take, so in particular this family of codes is called the Reed-Muller codes. They were invented by Reed and Muller in 1950 or so, and they have 3 parameters associated with it: Q denoting the field over which you're working. It will also be the alphabet of the code, so the code words will be vectors in FQ to some n. There will be a degree parameter d, which says what is the degree of the polynomials you're working with, and the m is the number of variables that you're working with over here. So the messages are the set of all polynomials in m variables over FQ whose degree is at most d, and the encoding is the evaluation of these polynomials at every point in FQ to the m. Okay, so these are codes of length n equal to q to the m, and the message space is as large as it is. We will discuss this in a minute. So what makes these codes locally decodable? It turns out to be the following very simple phenomenon. If you take a low degree polynomial, let's say the degree is smaller than the field size, and you restrict this function, this polynomial function, to any line, then you get a low degree univariate polynomial. So you have some non-trivial constraints on what the function values can be on a local set, and this translates to all the local decoding and correcting effects that we care about. Okay, so and a particularly useful fact about this is that if you look at a random line in FQ to the m, it's a collection of random points in space, a collection of pairwise independent random points in space if you care, and this is another fact that we will often use. So in particular, if I say fix a point x and let's look at all the lines through this thing, well, these lines will be going through a collection of more or less random points. Okay, so they more or less sample this space pairwise independently. Okay, so these localities immediately translate to a very simple decoding algorithm. So how do you get locally correctable codes and testable codes from polynomials? When the degree is less than the field size, the decoding algorithm is very simple. So let's look at the decoding problem. What is it? The problem is you're given some function f, m-variate function, mapping FQ to the m to FQ, and it's supposed to be close to some polynomial p of degree at most d. Okay, and given that it is close, what you're also given is some point alpha in FQ to the m, and you're saying what is p of alpha. Okay, so that's the question. So the decoding problem is stated on this line. You're given a function f, this is the oracle, there is some nearby polynomial p of degree d, and you're also given a point alpha. You want to find out p of alpha. You don't have oracle access to p, otherwise this would have been trivial, but with oracle access to f, this is almost trivial.
So f is x, p is y, and alpha is I.
Yeah, very good, thank you. Sorry, I mean it just, up to now that made sense. Now this is what will make sense for us. Sorry about the notational switch. The decoding algorithm just does the following thing. It picks a random point beta in FQ to the m, and it looks at the line capital L, which is all the points. I'm sorry about this line break here. About all the points of the form alpha plus t times beta, where t is an element of FQ. Okay, so this is a collection of points which come from a univariate line. And if you look at p restricted to the line, you should get a polynomial of degree at most d. F restricted to the same line is with high probability going to have good agreement with p. Okay, and you can argue this out formally using sort of simple Markov's inequality and so on. And once you have that, you notice that, so what I'd like to do is do the decoding problem restricted to this line. And this is a decoding problem that we know how to solve. We don't care how it's done, it can be done. So what are we going to do? We are going to find this polynomial h in one variable on this line which agrees with f restricted to this line, and then we will just take the value of this polynomial at the point alpha, whatever it is supposed to be. So think of this polynomial as sort of a function mapping the line to fq, take the value of the polynomial at alpha. This is a good decoding algorithm. It's easy to prove that it works. Now what about testing? Testing, well, it's even simpler to describe the test. You just take this function and restrict it to the line, and you verify that the function restricted to the line that you have is a polynomial of degree at most d. It should be true if you were a code word, and we hope that if f is far from being a polynomial, then on random lines it won't look like a polynomial. Okay, so this is the test. So these are the decoders and the testers, and what kind of parameters are we getting? So n is q to the m or whatever, but the locality is q, right, because at most you looked at the value of a function on a line, and a line has q points. So as a function of n, the locality is n to the 1 over m. Think of m as a large constant, and this is the regime that we are mostly interested in the talk today, but so that's significantly sublinear in the length of the input, but you're getting you're managing, if assuming we can analyze this decoder and the tester, this is a sublinear algorithm for testing and correcting. The rate of the code as we get this way is 1 over m to the m, and this is one of the parameters that we will be trying to focus on. In particular, I mean, it's roughly this when m is getting large. Even if you set m to the least non-trivial value, which would be 2, the best rate you would be able to get by this entire process is 1/2. So prior to about like 3 years back, there was nothing that we knew that would go beyond 1/2 over here in the rate for any reasonable locality, and that's sort of the direction which we want to go today. So given the simplicity of the decoding algorithm, the testing I didn't analyze the correctness, and one could imagine maybe the analysis is somewhat hard. So maybe the testing requires a paper, the decoding should be a footnote in that paper, and it should be done. There were actually sort of, if you look at the history, there were over 20 to 40 papers written on this particular topic. So what all were they doing? Let me tell you a little bit about what all were they doing. When the degree is less than the field size, which is the setting that I've been talking about so far, there were lots of works trying to correct more and more and more errors, and in particular you could look at the setting where d is sort of negligible, d over q is little o of 1. So the code has relatively little message thing, but very good distance, nearly 1 minus, so the relative distance is 1 minus little o of 1. Then you might want to ask, so can we correct 1 minus little o of 1 fraction errors? And a long sequence of works sort of ended up with some work with Trevisan and Vadan, where we could show that you could correct roughly this fraction of errors locally with this q local algorithm. Okay, so the fraction of errors is almost 1 minus square root of d over q. This is the best that's known so far, and sort of beating this would still be considered interesting. When the degree is greater than q, then you can no longer get any interesting information by taking a function and projecting it to a line. Okay, but that doesn't stop us. We could project it to a 2-dimensional surface or a 3-dimensional surface, and whatever. You can project it to an appropriate number of dimensions. At some point you will get some local constraint. Okay, and at that stage you can start getting local algorithms. So let me just tell you what kinds of results are true. By the way, I mean, as you can see, I have about 25 slides and we're going reasonably fast, so if you want to ask me questions and so on, feel free to. Okay, and I don't have a lot of details on the slides, but if you need anything to be sort of, you want elaborations on anything, I can tell you about them. So if the degree is greater than the field size, then you can still analyze the distance of a code, and this is in fact the original Reed-Muller paper had q equal to 2, so presumably d was larger than q, and in fact that is what it was, and what they used was the fact that such a code had distance roughly 2 to the minus d because q was equal to 2. In our case we will say for general q it is roughly q to the d minus d over q minus 1. I will tell you a little bit about where this number comes from in a couple of slides. And how you can do the decoding is by projecting the function to roughly d over q minus 1 dimensions, plus or minus. By roughly I mean plus or minus 1 or 2, not a factor of 1 or 2. It is this many dimensions plus 1 or 2 thing would start giving you non-trivial constraints. So you project your function to this space. It is a constant dimensional space if you think of d and q as constants and m as the only parameter going off to infinity. And this kind of analysis, now you can ask how many errors can you correct, and the locality, if you project to this many dimensions, then the number of points you would be looking at would be q to the power of the dimension. So that is roughly 1 over delta. So the locality is roughly 1 over delta. This is what you can get. It is fairly easy to correct from delta over 2 fraction errors easily. That is what you expect in the unique decoding sense. If you have a code of distance delta over 2 fraction of errors, you can correct uniquely, etc., etc. That is easy, and that was probably folklore. But a very interesting series of works, Gopalan, Cliven, Zuckerman, Gopalan, etc., have been trying to push this beyond delta over 2 to go to somewhere arbitrarily close to delta itself. Okay. And this is very non-trivial, or the kinds of analysis that goes in here is quite interesting, and not everything is known. If either q or d is 2 and the other parameter is arbitrarily large, you can do this. But when q and d are both say 3, we do not know how to correct from the delta fraction of errors. Okay. So this is already open at this stage. So correcting the right fraction of errors is correcting some fraction of errors we know how to do. Correcting the right fraction of errors, or what is the right fraction of errors, we do not know. Right. We do not know whether you should be trying to decode from delta fraction errors because the number of words at that distance may be super polynomial, super constant. But if we can prove one or the other, we should like to, yeah.
I take it this is those works about list decoding.
Right.
For unique decoding, do we have optimal results?
For unique decoding, yes, because you can actually correct all of these codes not only up to the unique decoding radius. Optimal, I mean, I do not know if they make exactly 1 over delta queries or is 1 over delta square queries, etc., etc. You can go up to the unique decoding radius, no problem. You can go beyond the unique decoding radius up to the so-called Johnson bound, which is a point up to where we know that if you try to list decode, you will not get too many solutions. And then beyond that, we do not know. For various special cases, we do know we can do better. So the Johnson bound does not have to be the bottleneck, and it's sorry. So this is just for those who know what the Johnson bound is. It probably answer makes sense. All right. So this is sort of roughly where the decoding of polynomials lies. What about testing of polynomials? The very early works, and this particular task had sort of significant impact on the construction of PCPs in the early days, and probably even now, I think all except maybe one construction due to Orr here have all used some significant statement about polynomials and their testability. If you want to get the best kinds of PCPs, they have all used some significant results on low degree testing.
Actually, if you are willing to take, say, square root n number of queries, then there is also a construction due to Widerman
that does not use polynomials. That might be even more recent than your stuff that I am talking about. Okay, so yes, it's all happened in the latest generation of folks. Okay, so over here, many results try to get, so you're thinking of the degree as being significantly smaller than the field size, and the challenge was trying to say that, look, if the test occasionally accepts, says you pick a random line, you ask the question, are you a polynomial of degree d or not? if there is an even non-negligible chance that you accept this thing, we would like to say, well, that's because there was some polynomial nearby, okay. And you can prove results of that nature. So it was done by Raz and Safra, and then in some work with Sanjeev Arora we did the same thing, and these are from roughly 15 years back and so on. So this is what happens on one extreme when the degrees are very, very small compared to the field size, but these are all results where you tend to think of both of these as growing and so on. So now when the degree is much larger than the field size, I mean these kinds of results will also apply when the degree is smaller, but it's just that they won't look impressive. But even when the degree is larger than the field size, you can do something, because we just noticed that there is some locality in the codes themselves. So what can you do? It turns out now you have a sort of a new quantity called the testing dimension. I'll call it T, which is the degree divided by not q minus 1, which is what I had mentioned earlier, but q minus q over p, where if q is a field of characteristic p and p is a prime number, then that's the quantity that you divide by. Okay, so well, this quantity is somewhere between q and q over 2, right. So within a factor of 2 of the decoding dimension, you get this testing dimension. So you take your function, you project it to a t dimensional subspace, and then you ask the question, is this a polynomial of degree d? Okay, so clearly it's a legitimate question to ask. Every polynomial of degree d would satisfy this property. The converse is the big challenge, and over here in this one simple thing I've sort of compressed two streams of work. What we know is that this test is a good test and it can be analyzed and so on. It's clear that such a test would make q to the t queries, because you take a t dimensional subspace and you look at the function over there. The early analyses said, well, okay, it also has some non-trivial soundness, in the sense if you were 1% far from being a polynomial of degree d, then you would detect it with probability something like q to the minus t. Okay. And a pair of works, one which was joint with Bhattacharya, Swastik, and Zuckerman and Schoenebeck. I think I got everybody. We were able to show that you can actually, if you're 1% far, you reject with some constant probability. You actually, and that was over the binary field, and then later work with Haramati and Špilka, we were able to get this to work for all constant field sizes. These two works are sort of, they were a nice alternate way of looking at low degree testing and analysis there. But anyway, so we have these kinds of results. So what did I want to say next? Okay, so all right, so the thing that I want to tell you, so firstly this is roughly where the state of the art is. By the way, over here I would love to see some very nice number epsilon sub q. It's probably the case that if you're doing low degree testing over a field of size q, there will be some dependence on q over here. Not particularly clear why, but maybe, I mean, I could allow for that. The dependence that we are able to get in this epsilon sub q right now is some sort of an Ackermann like function, and that's really bad, and it sort of shows up in various other places where we would like to see some better analyses over here. In general, also something that I'll dislike is that there's sort of very different collections of theorems and proofs in the d greater than q setting, and very different collections of theorems and proofs in the d much less than q setting. One of the goals of some of my works has been to try to get a sort of an umbrella of theorems which somehow covers both sets of cases, and this is sort of what I call a fine invariant codes and testing and so on. But anyway, we haven't gotten such results so far. This is roughly what we know about the testability. I just want to talk a little bit about this testing and decoding dimension. Where did these two numbers come from? Why is the decoding dimension d over q minus 1, and why is the testing dimension some number which is even uglier and larger? So recall, what is decoding dimension? I'd like to say here is a polynomial of degree d, I would like to sort of project it onto a small dimensional space so that I get some non-trivial constraints on this function. Okay, I have a function supposed to be a polynomial of degree d, I would like to project to some non-trivial dimension. Now if I look at a function on fewer than this many variables, it is a polynomial of degree less than or equal to d no matter what. In each variable your maximum degree is q minus 1, you have less than so many variables, your total degree is less than d. So looking at fewer dimensions won't work. The first instant of time, the first value of t for which you have functions which are of degree strictly greater than d gives you a non-trivial constraint. On this t dimensional subspace your function cannot be an arbitrary function, it is constrained. And symmetry now tells you that there will be a constraint involving any point that you care about. Okay, the entire affine space is symmetric around any one point. So there will be a constraint involving this one point, and that is it. So decoding dimension is d over q minus 1 for a very nice obvious reason. Okay, does this make sense? Okay, so this just says this. Now why is the testing dimension this much weirder quantity? Okay. And let me not give you the full analysis, but let me go to a particular case. So I will consider q to be a power of 2. In that case we would be saying that the testing dimension should be something like twice d over q rather than d over q minus 1. Okay. Why? So let us take a look at a very simple function f, which is x to the q over 2 times y to the q over 2. Okay. This is a polynomial of degree q. Okay. I want to claim that it actually looks very different on every line. What happens? So on consider a line y which is ax plus b, let us say this is just a function of two variables, x and y are the only two variables. Okay. So on the line y equal to ax plus b, this function what does it look like? It looks like x to the q over 2 times ax plus b to the q over 2. Okay. So that is fine. Now this is where behavior of the prime characteristic comes in very important. Q over 2 is a power of 2, 2 to the s minus 1, and powers of 2 sort of slip through the parenthesis in these kinds of expressions. Okay. So that turns out to be, this guy turns out to be equal to a to the q over 2 x to the q over 2 plus b to the q over 2. Okay. I just did the natural expansion, and then you expand this out. Well, the first term is a to the q over 2 times x to the q, but x to the q is the same as x. We are working over a finite field of characteristic q, x to the q equals x, and plus b to the q over 2 times x to the q over 2. So the degree of this polynomial is q, but it looks like a degree q over 2 polynomial on every line. Okay. So you, of course, I mean you are looking at polynomial of degree q, no line is going to reveal that it is a polynomial of degree q. I mean every function on a line is a polynomial of degree at most q minus 1, but you might have hoped that you would get some terms of degree q minus 1 or q minus 2, and it is not happening. You are immediately jumping down from q to q over 2. In general, if you were working with characteristic p, you would jump from q to q minus q over p in this kinds of formula. Okay. And that is the reason why you cannot sort of, you do not divide by q minus 1, you divide by q minus q over p. That is the maximum degree you can force on every variable, and so this is turns out to be the right number to look at. So this kinds of facts we had actually known for many years. So this particular example probably goes back to a paper that I wrote with Cathy Friedel in 95. The exact testing dimension was analyzed much later by Kaufman and Ron, maybe about 2004, and this is roughly where we stand. We always knew that testing over non-prime fields is sort of in some senses worse than testing over prime fields. If you were working with a prime field, then this quantity q over p would be 1, you test with smaller number of test points. On the other hand, if you are working with a prime non-prime field, you have to go to a larger number of project onto a larger dimensional space, and so you are wasting your queries. So that was the moral, and roughly we want to change the story today. All right, so just by the way, another interesting thing, you could say, look, okay, I know that my function, I can reduce it to the minimum dimension where it reveals the property that it's not a degree d polynomial, or where every function would reveal of degree greater than d would reveal that it's not a degree d polynomial. So that's the testing dimension. But maybe testing with a few extra points of an extra dimensional space and so on, maybe it would be advantageous. And so far we haven't come up with a single scenario where this is really inherently useful. The only case where I think this has been useful was a work of Raz and Safra, where they said when we are testing polynomials of degree d which are much smaller in degree than the field size, it's better to test by projecting onto two-dimensional surfaces rather than a univariate line. The analysis is very clean, very general, and so on. So except for this one case, I mean, it's never really sort of paid any dividends to say, let me use a few extra queries, but maybe I get a much better analysis. It doesn't seem to be working out. Okay, strange, but that's the way it is. All right, so polynomials are not the only codes, local codes that we know about. So what are the other ones that we know? In general, you can get polynomials are not the best codes, locally testable codes, but by composition and other things that you can do with codes, manipulating codes and massaging them and so on, you can start with a code which has some sublinearity in the testability and reduce the sublinearity down all the way to very small numbers, even 3 queries suffice, etc., etc., which are without too much of a loss in the rate. And there's a lot of work going into this thing, but that certainly, so the locality parameter, somehow we can sort of, once you get into some good sublinearity, you can start pushing it down all the way. But no matter what locality you wanted, as long as it was little o of 1, till recently we didn't know of codes which had rate greater than half. You don't know how to get any sublinearity with rate. We didn't know how to do that. On the locally decodable side also, till recently, I mean, not quite true, but there were a couple of examples, but multivariate polynomials were close enough to the best known locally decodable codes. In 2007 and few subsequent years, Sergey Yekhanin, Prasad Raghavendra, and Klim here had great improvements in the small query regime. So if you want to build codes which have locality 3, so you make 3 queries and you test whether a code, you want to decode codes with 3 queries, etc., you could get vastly improved results, but still at this stage the length of the code is definitely significantly super polynomial in the size of the message. Okay. Getting better is open. Possibly they don't exist, but we don't know how to prove such things. And the rate half barrier also survived for till 2010, and then Swastik and Shubhangi and Sergey came up with these codes called the multiplicity codes, which I won't describe today, but they're very pretty, very simple also. They get rates going to 1, and the locality can be made an n to the epsilon for arbitrarily small epsilon. So you pick a constant epsilon, you can get this. And so these were the first codes to go beyond rate 1/2 with some locality in it. Somehow the original sort of view, I think before the result, at least the mental picture I had of locality was, yes, I mean certainly, I mean given that every point is involved in some sort of a redundancy, rates cannot be particularly high, and this it was very surprising when this kind of a thing happened. So these are settings: very low queries or very high queries, n to the epsilon or constant. Locality, if these are the localities you're thinking of, we can do better than the multivariate polynomials. Multivariate polynomials are still the best locally decodable codes we know of if you're thinking of some interim range of parameters, if you want to make some polylogarithmically many queries. What's the best code we have? Still the same old. I mean, we haven't improved on that at all in this over these so many years. Okay, so this is still a pretty interesting challenge. Can we do something better over here? No, we don't have any ideas.
So are there bounds, low bounds?
I'm sorry?
Are there low bounds? If you're given a period of time
Right. So, are there lower bounds? In the locally testable codes, no lower bounds at all, and probably, I mean, you could ask the question, can you have locally testable codes of constant rate which with 3 locality of 3? As far as we know, I mean, locality of 3 is a very special thing, but as you allow the locality to be a constant but getting larger and larger, these may be competitive with the best known codes that we have. There is no real separation known between rate and the relative distance. So, in locality in testing, no lower bounds whatsoever almost. In locally decodable codes, there was a work by Katz and Trevisan, and then maybe some minor improvements after that quantitatively, and they tend to say that if you want constant locality, then your n must be k to the 1 plus epsilon, some positive epsilon for every locality. So, even if you ask for locality 3 queries are allowed. The highest lower bound we have is n square, and if you allow the number of queries to go up to log n, then the codes could be of linear rate. So, okay, so the lower bounds are there, but they are very weak. They are strong enough to say that locally decodable codes are a stronger concept than locally testable codes. Okay, so n is k squared, right? Yeah, sorry, n is k squared, correct.
Locality Q is not the only place where known the good lower bounds where it's exponential.
Locality 2, right? With locality 2, we know that it's the n has to be exponentially large in k, but that's the only setting. Thanks. Yeah, good. 3-query local testing, no, 3-query local testing. We have codes of nearly linear rate n polylog n. Yeah, so. Over here, I don't know what I might have meant by that. Okay, sorry. All right. Okay, so polylog n, you log n already you could have linear rate. At log n, we don't even know of polynomial n which is polynomially growing in k. At exactly log n, we don't know it, and no reason why we can't, so on the one hand we don't have a polynomial upper bound, on the other hand we don't have a superlinear lower bound. Okay, so it's pretty vast, the gaps over here. So today what are we going to do? We're going to give you locally correctable and testable codes from lifting. Wow, so I'm really going slow, is it? The rate of these codes is going to be again approaching 1, just like in the construction of Swastik and Shubhangi. The locality will be n to the epsilon, again similar. The one advantage we seem to have is that, at least as far as I know, and I think Swastik is working actively on this to see if the multiplicity codes are testable or not, we don't know that they are testable so far. Is that correct, Swastik? Okay, and whereas our codes will be sort of naturally testable as well as correctable and achieve all of these parameters, and these are only, if you want only local correctability, these are only the second codes with this property. After the only previous example was the result from 2-3 years back due to Swastik and Shubhangi and Sergey. So what are the codes? At least, okay, we won't go away without knowing what the codes are. Let me tell you what the codes are. So the alphabet will be some finite field as usual. The coordinates, the length n will be associated with fq to the m. We'll give a degree parameter d, and the space of messages is just all functions which, when restricted to various lines, to every line, have degree at most d. Okay, and the codes will be evaluations of these polynomials over the whole space. Okay. So as I've stated so far, this is almost exactly how we described multivariate polynomials. The set of multivariate polynomials have this property. Okay. And the only thing that we are going to change, on the one side we are going to make sure that the fields are of small characteristic, in particular let us say 2 to the s, and the other is that the degrees that we will be looking at are not going to be less than q over 2. If the degree had been less than q over 2, then we know that the set of the message space is the set of degree d polynomials. Now we are just going to let the degrees be larger, tending to q rather than tending to q over 2, and we are thinking of m as a constant, so any dependence on m might be missing in my talk, but that's. So recall we had this bad news, when you take a function of degree greater than, we had functions of degree q, we restricted it to many lines and we were getting functions of degree q over 2. We said this is bad news, this forces us to test using higher dimensional projections. But if you flip the picture around, this is actually very good news, because it says if you look at the space of all functions which have degree less than q over 2 on every line, this includes all the degree q over 2 polynomials, but it also includes a superset. So your message space has expanded rather, so that's the way to think about it. Rather than obsessing over the polynomials and saying I want to test them, we want to say let's look at, fix the test and see what is it testing, and whatever it tests is what we are happy with. Okay, so the rate is higher, and does this make a quantitative difference? You know, x to the q over 2, y to the q over 2 sounds like a very, you know, special monomial, and the difference is really overwhelmingly large. I mean, we are getting most of the dimension from these spaces. Okay, so this class of codes came from a sort of a slightly more general family that we were studying, and I want to tell you about this more general operation. We want to start with a small code and build a bigger code, so small code B and build a bigger code C from it. And how do we want to do this? The base code is given by, you know, t-dimensional functions. I am allowing the field size in the domain to be different than the field size in the range, but think of them as the same for now. And what we will insist is that this codes, the set of functions that we are considering here, is invariant under affine transformations of the domain. That will be the right way to do it. So the thing, for instance, the set of degree d polynomials could be the base code B, okay, which will be invariant under affine transformations. The lifted code, the m dimensional lift, is just the set of all m variate functions which when projected to t dimensional subspaces give you functions that sat in B. Okay. So this is the definition of lifting. I hope the definition is clear. All right. So
Is it crucial that you use an extension field of
no, it's not. For most of what I'm going to describe, you don't, better to think of the two as the same, though there are some interesting examples where we like this guy is a binary field and this guy is larger and so on. Okay. And in the previous example, what did we do? We just took this to be a univariate polynomials. The base code was univariate polynomials of degree at most d, and the lifting was defined accordingly. Okay. So what lifted codes give us a lot of nice properties just naturally without exploring what is the code you're lifting, etc., etc. For instance, the distance of the lifted code will be more or less the distance of the base code. Okay, so you lose a little bit and again a little bit of the loss, but you know you can ignore pretty much all of this. It's more or less what you started with. Okay, the local decodability is trivial. The decoding algorithm that I gave you earlier for polynomials was a decoding algorithm for lifted codes. It had nothing to do with polynomials whatsoever. Local testability turns out is, I mean the test is quite natural. You know, what would you test? You would say pick a random subspace of dimension t and verify that your function restricted to the subspace is from the base code. Okay, the test is natural. Turns out that this way of looking at it is what we would call a single orbit characterization in some work with Thale Kaufman. So it's actually, this is a test that works. Actually, we can prove that this would make q to the t queries. Why? Because that's the size of the that's the length of the base code, and you can prove some soundness of that. And in fact, there is an even better analysis now in some joint work with Elad Haramati and Noga Ronzevi, and you can actually also show that this the improved analyses that we had for low degree polynomials or moderate degree polynomials also works in this setting. So pretty much anything that we knew about testing, many of the things that we knew about testing works also for the lifted codes. There are some issues that these are good open questions over here, but let me not go into that. We're running close to out of time.
Okay, 10 minutes then, but there's a
Yes, Clem?
First encoding is easy, so
Sorry?
to encode a message in this lifted code.
So given that we decided to skip encoding in the first slide, I haven't thought about it since then.
It's a linear space.
It's
so
a, yeah.
linear space. So once you have a basis, it's
First of all, to understand what's the basis is not clear how.
no, but that's something you do. You just have to understand what the basis is.
Right, yeah.
Then it will be
Right, so there is actually enough structural theorems to understand the basis also and so on. I didn't talk about it much. In particular, I mean, if you, it's actually there's exciting things that happen when after you've understood what the basis for B looks like, to understand what the basis for C looks like is interesting and challenging, but only as a closed form analysis question, not as a computational question.
No,
Yeah.
because I think it's interesting mathematician math question. So
Right, there are lots of interesting mathematical challenges there, but I think the lifted family is easy to understand given the base family is really easy, and the other things are understanding base families for given constraints or something maybe.
So for the base codes, all what matters is the parameters it has, the distance, the dimension?
No, you can pick any affine invariant code, any code which is invariant under affine transformations, and there is a richness over there which we don't understand fully. So we'd been sort of struggling with the lifted concept, what codes to lift for a long time, and after trying all kinds of complicated things, suddenly realized that, oh, if you even lift the parity check code, you get very interesting results. I mean, and the Reed-Solomon gave us the results that I described. So it's possible to try other things. It's not just one parameter that tells you what's the base code.
and for these small lifted codes are coincide with nելnϵ or not?
For D small compared to T,
Compared to Q. When degree is smaller than Q, does it solve?
right, yeah, if the degree is less than Q minus Q over P, then it is but by degree you mean that the code is defined as the set of polynomials of degree at most D. Even within that space you have further choices of saying which monomials of degree less than D do you want to choose. You don't have to choose all of them. So you could improve the locality of your codes by making its rate slightly smaller, and such examples are known actually.
No, I'm asking about like if you are taking lifted code when on each line it's of degree of small d, does this lifted code is
Yeah. That is Reed-Muller, right? Yeah. Okay. So like I said, so the lifted codes distance is fine, the local decoding testing, every property that you want about them is fine. The only thing that actually requires individual examination is the rate. How do you know what is the dimension, what is the basis of this code? So there's no generic analysis, but we have enough structural theorems which basically tell you the following. If you want to find out which codes are in the lifted family, you have to basically ask just the following question: which monomials are in the lifted family? So not general functions, but just the monomials. So let me give you an example, and this is so in a couple of pages I think I'll be done with the analysis, or as much of it as I want to show. So here is an example where I want to show to you that I get bivariate polynomials where the rate is tending to 1. So my base code is going to be all functions of degree at most D, and I'll let D, this epsilon, D will be 1 minus epsilon times Q, and epsilon itself I'll set it to be 2 to the minus C, and I want to understand this as epsilon goes to 0, which means C is going to infinity. Okay. So after I let C go to infinity, I'll let Q go to infinity even faster, but never mind. Okay. So that's the general thing. Now here is what we want to understand. So we want to understand what are bivariate polynomials which have the following feature. So let's even focus on a monomial x to the I, y to the j. If I give you enough different monomials, then every linear combination of these will also be in the space. This is a linear subspace. What are the monomials for which x to the I, y to the j is in this code C? Meaning, when can I sort of set y equal to ax plus b, and then notice that x to the I times ax plus b to the j is of degree less than d, but why would the degree reduce at all? Well, because we are going modulo x to the q minus x, right, because we are working on a field of characteristic of size q, we have to go modulo this, and so if I plus j is greater than q, then the highest degree term for instance drops in degree. Other terms may or may not drop, and we have to see what happens. So this is the question that we have to understand. So let me try to tell you about one basic theorem which helps us explain this. We want to understand what happens to ax plus b to the j when you expand it. What are the different terms that come up? If you had been working over a prime field and j had been less than the prime, all the terms of degree less than j would appear over here. But if you are working over a non-prime field, then not all the terms appear. And which ones do? Well, terms of degree r will appear if and only if the following condition holds. You write r in binary, you write j in binary, and in each binary location, say r sub I is the ith bit of r and j sub I is the ith bit of j, r sub I should be less than or equal to j sub I. So these two numbers are both zeros and ones. You can take a 1 and convert it to a 0, but you cannot take a 0 and convert it to a 1. So not every term of degree less than j will appear here. It's some strange things in the binary expansion of j which dictates this. Okay. So this thing tells us that not everything applies. So now we have to say, okay, so what happens when I have ax to the b to the I, sorry, x to the I, ax plus b to the j. I'll write them down in binary. The least significant bit is there, the most significant bit is here, and I want to say, well, when does a term of degree u appear over here? Okay. And what would be bad is I and j will not be acceptable if I can come up with some element r which is bitwise less than or equal to j, where when I sum these up modulo x to the q minus x, all these bits are 1. Okay. Because what does it mean for the degree to be less than 1 minus epsilon times d? The c most significant bits are all 1s. Sorry, d to be sorry, what does it mean for d to be greater than 1 minus epsilon times c times q? Means all the c most significant bits are 1s. If any of these bits is 0, then this degree u is not a forbidden degree, it's okay. So that's what I've written down. So if I can find some bit where this thing is 0, then I'm okay with this ij so far. Okay. So if for every r that is less than or equal to j in our binary sense, if it turns out that I plus r when I write it down has some 0 over here, then I'm in good shape. So what would make one of these bits go to 0? What structure in I and j would make one of these bits go to 0? Well, here's one simple thing. Suppose you consider these 4 bits and they are all zeros. There is no way of adding these numbers, and by the way, going mod x to the q minus x will just say that there is a, when you add these two numbers you get a carry and you add that back here. Okay, so it's a rotating carry, you don't know where to start, but doesn't matter. So that's the thing. But if these 4 bits are 0, this carry etc, nothing matters. You're going to add these two numbers, at most you get a 1 over here because of the carry that you had, and so you're not going to get 1 over here. What's the probability that when I pick I as a random exponent and j as a random exponent, I get these 4 bits to be all zeros? Well, the probability that I don't get this pattern is at most 15 over 16. But now I have c over 2 such potential locations. Let's look at every alternating bit over here. Each one of those has sort of a 15 over 16 probability that this thing is not this all 4 0 pattern.
Why c over 2? Don't you need all c of the,
No, I need only one, and so just to make these events disjoint, I just say okay. So you can even get a slightly better bound, but this is certainly good enough. So what's the probability when you pick I and j at random that there exists? And by the way, once j is 0 here, there's not much you can do in r in these coordinates. You can take r and you have lots of variation what you can do here and here, but r has to be 0 here. So I plus r really looks like this. And so what's the probability that I and j end up being greater than d in this x to the q minus x mod thing, since it's just 15 over 16 to the c over 2, and this is a quantity that's going to 0 as c goes to infinity. So the rate, what x to the I and y to the j can I pick? Well, when I pick I and j at random, the probability that it's a forbidden pair is going to 0, the rate of the code is hence going to 1. Okay, that is the analysis. So that is all I will do. You can sort of do this analysis for m variate polynomials, and you get some log m bit sequences have to be examined, and you have m of those, and so the exponent, this quantity has some m log m's and so on and so forth sitting there, but okay, the behavior with larger m is not great, but you get what you want, which is codes of rate n to the epsilon for any epsilon you want, and rate is going to 1 for all those epsilons. There were some other fairly interesting locally decodable codes that we could find, but let me skip this thing. And can I take 5 or 10 minutes? All right, okay. So let me just give you one neat application in sort of this combinatorics to this concept called Nikodym sets. And here is a notion. Set is called a Nikodym set if it sort of almost contains a line through every point. Okay, so n is a subset of points in space, m dimensional space. For every point A, you want to say there is a line containing A. So some direction B says that when you look at the line containing this thing, it would be stupid to ask the question, well, for every point A, this set should be contained in n, because that would be saying for every point A should be contained in n. So I allow you to make an exception on A may not be contained in the set, but all the other points in the line should be contained in the set. Okay, does this make sense? So this is the challenge. So how small can a Nikodym set be is a question that apparently was asked. It's sort of similar to the concept of Kakea sets with which Dwyer and Avi also looked at in constructions of extractors. Kakea sets are supposed to contain a line in every direction. This is the most sane description of a line in through every point. Okay, and the Kakea set formally is defined here. The main differences are that the quantifiers got flipped. For every direction there is a line, and of course we had to make this distinction. Okay, so this is the notion, and if you look at so there was this celebrated result of Zaev's with some follow-ups with Swastik and Shubangi here, which show that when you look at the size of the Kakea sets, and the same proofs apply also to Nikodym sets, that these have size at least q over 2 to the m. Okay. The point that I want to make mainly in this talk is firstly that the entire analysis that we saw over there was really about locality and about local testing, more or less, local characterizations. So what was this proof which led to something along these lines? I will give you roughly Dwyer's original proof applied to Nikodym sets, because it will be the cleanest and simplest. So how do you prove that a set n has to be very large? You use polynomials. And how do you use polynomials? You say find me a polynomial which is not identically 0, it is an m variate polynomial, but it is 0 on every point in the Nikodym set. Okay. So find what can we guarantee? Well, you can guarantee that the degree of this polynomial will be at most q minus 2, provided the number of points is less than m plus q minus 2, choose m. Why? Because you look at how many degrees of freedom do you have in the choice of p, and the degrees of freedom will be more than the number of points, and you have one linear constraint for each one of these guys. Now you can say, well, but now this polynomial restricted to every line is 0. Why? Because the polynomial on this line has q minus 1 points from a Nikodym set. A might not have been in there, but all the other points were in the Nikodym set. It is a function of degree q minus 2. So it is obviously 0 on this line, but if a polynomial is 0 on every line, it is 0 on every point, it is 0, and that contradicts the fact that p was supposed to be non-zero.
Every line relevant to the Nikodym property.
Right. Oh, sorry. For every, sorry, okay, good. I should say this is for every line that was used in the Nikodym property, but then in particular it is also 0 on every point. Okay, it's being 0 on every line implies that it is 0 at every point, every one of those lines, because those lines, the union of those lines covers all the points. Okay, sorry, thanks. Okay, that was I've forgotten that. Anyway, so there is a contradiction here. What was the assumption? The assumption was that n was small, so n is large, and this gives you a nice lower bound, and if you do a lot more work you get n is at least q over 2 to the m. Now if you now ask the question, what did we need from this polynomial p? Why did we need this polynomial p? There are only two things that you asked for. One, this dimension of space of functions that you are working with should be sufficiently large, and polynomials give you sufficiently large dimension. And the other is that this polynomial, when restricted to a line, is low degree. We never asked that this polynomial should itself be low degree, we just said when you restrict it to lines it should be low degree, in particular the lines relevant to the Nicodim sets, but if you get that it is a low degree polynomial restricted to every line, that is sufficient. So if that is the case, then we should not be picking p to be a polynomial, but rather a code word of our lifted code, and if you do that, then you get a lower bound on the Nicodim sets, which is sort of 1 minus little o of 1 times q to the m. So the size of the Nicodim sets is not a vanishing fraction of the whole space, but an overwhelming fraction of the whole space. Okay, so this is what we get. And that is the funny thing. So if you had replaced, so what is the difference between Dweer's proof for Kakeya sets and the Nicodim proof over here? There is some hairy technical thing saying, oh, by the way, when I look at the highest degree term in this polynomial, it is the same as the highest degree term in some other polynomial, and so on. There is some little bit of a technical ugliness which nobody wants to talk about. If you do not have that ugly technical condition, you would have proved the same lower bound for Kakeya sets. And yes, in Kakeya sets we know that q over 2 to the m is the right growth, whereas for Nicodim sets we do not know that it is the right growth. We know it is the right growth for q of small characteristic. If q is large characteristic, again we do not know. What if q is a prime? Maybe this is the right answer, this is the best that we know. So it is a very strange situation. If you think of these finite fields and lines over there as not being very different, you would really suspect you should be able to prove this for other fields, but then how, we do not know. So anyway, so there is some neat consequences for these lifted codes, and let me wrap up by just saying, okay, they seem to be extending this family of low degree polynomials nicely, and one of the nicest things is we have almost not found, I mean you can pretty much box sort of draw very clear boxes about 3 results in the literature which probably used special properties of polynomials. And almost everything else was just lifting as far as the locality properties of polynomials we have used. So most of the features remain the same and the rest are just open. I mean it is not like we know that there is anything very significantly different about lifted things, and it leads to new codes. And in general there is a sort of broader class of what I call affine invariant codes invariant under affine transformations, which seem to be possessing a lot of the underlying structure of polynomials and the tools that come with it, and they seem to be very much worth exploring. In particular, I mean maybe if you are lucky, whoops, we could get some improvement on multivariate polynomials in the polylog locality regime. We do not have linear sized codes with such locality. Maybe this is a place to look for them. Okay. All right, thanks.